Okay, so we are going to go through the derivation for chapter 28, section 5, magnetic field of a circular current loop. Now, in class, we talked about the magnetic field at the center of the loop. And you can use Faraday's law Ampere's law to figure that out, but we're going to use this equation again. And so we have a differential element on this loop. And that differential element is going to generate a magnetic field at some point here. And that point is along the axis of the loop. So it's equally spaced from all the points on the loop. Now if we let x go to 0, we'd be at the center of the coil. So this is just going, if you drew a line through the center of this coil and just extended it, it would tell you what the magnetic field is. And because every element on the top has a corresponding element on the bottom, and the element on the bottom is going to produce a magnetic field in the y direction opposite the one at the top, they're going to cancel each other out, and you can, at any point on this circular loop is going to have the same effect. So something over here is going to create a magnetic field going one direction. This one's going to go the other direction. And that's the z direction stuff. But they're all going to have this positive x component. So what we're going to do is we're going to integrate to get this dB sub x. So let's look at what the different components are, like we did for the magnetic field around a wire. So dB sub x is going to be dB, which is the total magnetic field vector, the magnitude of it, times the cosine of the angle theta. And the cosine, because the dB sub x is the adjacent side to the angle theta. For dB sub y, you'd have to use the sine of theta, but we're only going to worry about this one, which is the cosine of theta. And we'll be able to figure out cosine by this triangle here, because this angle theta, in terms of the magnetic field, is the same as the angle between the y-axis and the line that connects this differential element on the ring and the point in space. So what kind of substitutions can we make here? One is the cosine of theta is here's theta, so the opposite side is x divided by the the hypotenuse, which is r, but r is equal to x squared plus a squared. So we're using a as our y coordinate. We're not using y, we're just using a. That's the distance from the center of the loop to the loop. So that's the cosine of theta. And then we have r squared, which is x squared plus y squared. And this is r is equal to the square root of that, not just, so r squared is that. R squared is that, so r is that. So if you make those substitutions into it, dB sub x, the x component, is going to be mu 0 I over 4 pi. Now the dl is still a dl, okay? But dl is, when we integrate dl, we're going to end up with the circumference of the circle, because in this case dl is not either x or y, there's not that correspondence. So we're going to end up with x divided by r to the 3/2 power, or x squared plus a squared to the 3/2 power. So that's, if we take r squared times this r, which in this case comes from the cosine of the angle, we get r cubed, which is x squared plus a squared to the 3/2 power. And instead we have this differential. So then we can integrate it. So the integral of the x component, the total x component, so that's going to be b sub x, is the integral of this whole thing. But because we're not varying the distance, we're not varying this distance x for a given calculation. I mean, we could choose different values of x, but we're not integrating in respect to x. So this actually is constant. This is constant, this is constant. They're all constant. So the only thing we're integrating with respect to is dl. You know, with a wire we had this infinite distance. Here we don't have an infinite distance for the loop, so we just end up integrating dl, and the integral of dl around the circle is 2 pi times the radius. So we get mu 0 I over 4 pi times x divided by x squared plus a squared to the 3/2 power times 2 pi times the radius. I'm going to use a capital R as the radius, which I guess is a also, right? A, if we go back to the original drawing, the radius is a, so I probably should just put a in there. So that's it. That's the function. You can see that the pi's cancel out, and the 2 over 4 becomes 2. So let's write that. So the total x component of the magnetic field at some distance x from a coil that has a radius of a is mu 0 I over 2 times x divided by x squared plus a squared to the 3/2 power times a. Now, if we let x equals 0, or we're going to let x go to 0, what happens then? We have a problem. So what did I do wrong here? So let me just pause for a second. Okay, I found out what I did wrong. So it was right here. This should be A. If we go back to this picture, here's theta. A is the adjacent side. What I was doing was the sine, not the cosine. So this becomes A. So this becomes A. Through here. So yeah, why did I leave that in there? I'll explain in a second why I did that. Instead of, it was because I caught it. You know, this is the whole idea of, you get to a point where something doesn't make sense. You don't just keep going on and don't go back and check to see what the problem was. The problem was that if I had an x here and let x go to 0, the magnetic field would go to 0, and I know that's not true. So I knew there was something I'd messed up. So in this case, we're going to let x equal 0, which is the center of the coil. So you get mu 0 I over 2 times a over a squared to the 3/2 power times a. And so if you take a squared to the 3/2 power, you've got 2 times 3/2. Multiply the exponents together because you got one exponent raised to another exponent. So you end up with, in the denominator there you get a cubed, in the numerator you get a squared. And so if you simplify that down, you get 1a is still left in the denominator, so you get that. And that compares with what we came up with, what we talked about in class. The magnetic field strength at the center of a coil is equal to mu 0 I divided by 2. In our previous terminology, we used capital R to represent the radius of the coil. But in this derivation, we used A. So that provides additional support that we did this correctly.